6.3, Proving Identities. If you have not already taken the identities from section 6.1 and 6.2 and put them on a go-to cheat sheet for 6.3, I would recommend that you pause the video now and you do that. Having that handy and being able to reference it easily instead of flipping through multiple pages is going to make this a lot easier and a lot quicker as we move forward. So if you need to pause the video to do that, please do that now. All right, so now that we have that done, we're going to talk a little bit about what does it mean to verify versus to prove. So to verify an identity is to substitute in permissible or allowable values and ensure that the left side equals the right side. This only works for the values that you substitute into the equation. So if I plug in 5 and it works, that only proves that 5 is a reasonable answer for that expression. In order to prove an identity, you have to work strictly algebraically. So we're not going to have any numbers going in there that we're going to replace in for our variable. And this ensures that all possible values will result in a valid answer. So it means that I am meaning every single possible value is going to work instead of just a small handful that you're going to check individually. Now, as we move through proving identities, there's no one way that's going to work, and I have some suggestions to help you get started. We're going to go through these suggestions, and as we go through, we're going to try some of them out on different identities and explore how this might work. Now, keep in mind, there's not one way to solve these. So this is the way that I've solved them. It's probably one of the quicker ways, not necessarily the absolute quickest way, but it kind of demonstrates all the different pieces and all the different strategies that you can use as we're going through this. So the first one is to begin with the more complicated side of the identity. Typically, we like to start with the easy side, and that's something that is actually counterintuitive in this. So if you start with the more complicated side, it's easier to simplify it than to start with the simple and try and make it more complicated, because there's so many more things that we could do to make it more complicated. So always start with the more complicated side of the identity. Number 2 is if one side contains one or more indicated operations, so for example, addition, subtraction, multiplication, division, perform these operations and then simplify by collecting like terms. By doing that, we're actually going to save us a step, and it usually sort of works out some of the more complicated things to be a little bit easier. Example 1 asks us to prove that the following equation is an identity. Now, when I look at this, it's telling me this is going to work, show me how it works. So we know that this is an identity. I can interchange these two things. I need to see the in-between steps on how that goes. Now, you'll notice that I have this set up a little bit differently than how they've typed it. So I have the left-hand side of the equation over here and the right-hand side of the equation over here. And in the middle, I have a line. And so instead of using an equal sign, we use a line to sort of help us decide where the two sides are. And it just breaks it up instead of always searching for that equal sign, which can sometimes get lost in the middle of everything. Now, one thing you'll also notice throughout this lesson is sometimes this will be way over here. As we're solving, sometimes this has to get longer before it gets shorter. So you may find that sometimes it starts over here. That's okay, especially if we're only working on one side of the equation. That's going to help us out, have a little bit more room to work on. Now, the goal when I set up one of these equations is I want to turn these things here into this here. And I'm going to do that by using my identities. So I need to follow the above suggestions, as well as do a little bit of figuring out, I got red on this piece and I need red over here. Do those two pieces go together? So using that puzzle analogy, we're trying to find those common things that we can piece together. Suggestion 1 asks us to begin with the more complicated side of the identity. So this side is more complicated. It's got squares in there, it's got an addition sign, it's got more than one trig identity. That is going to be where we start our work. The second suggestion is if one side contains one or more indicated operations, perform these operations. So here I have 1 minus sine theta, and it is squared. So I'm going to start by doing that. So I'm going to focus right here. When I do this, I need to remember that this is squaring this binomial. It is not taking the square of each of those individually. So I need to make sure that I'm doing 1 minus sine theta times 1 minus sine theta. Now, there is a short form to learning how to do this without having to do a lot of work on the side. So the trick to squaring a binomial is to square the first term, multiply the two terms together and double it, and then square the last term. So when I do that, I'm going to get 1 minus 2 sine theta plus sine squared theta. Now, I haven't done anything with this plus cosine squared theta, so it's going to continue on into the next line. Now, I've expanded, I've used suggestion number 2. I need to somehow turn this into the right-hand side. So I'm going to look at my identities, and I'm going to look and see, what do I have there that I also see here? And what it jumps out at me initially is this sine squared theta plus cos squared theta. Now, that's helping me out because I know that's one of my Pythagorean identities, and I know that ultimately sine squared theta plus cosine squared theta is equal to 1. So this 1 minus 2 sine theta is going to stay the same, and instead of sine squared theta plus cosine squared theta, I'm going to write what it's equal to, which is just 1. Now I'm going to combine like terms. So I have a 1 plus 1. That's going to give me 2. So I have 2 minus 2 sine theta. I can factor out a 2 here. And as you can look, when I have 2 minus 2 sine theta, I'm starting to look really similar to this 2 times 1 minus sine theta. And when I factor out a common 2 here, I'm going to get 2 times 1 minus sine theta. So I have successfully proven that this initial phrase or expression is the exact same as the right-hand side. Now, we have a little special thing that we do when we finish this. And so since the left side of the equation has been transformed into the right side, this equation is called an identity. The letters QED at the end stand for the Latin phrase quaderat demonstratum, which means which was to be demonstrated. So basically, QED is something that we put at the end that says, woohoo, I did it. I managed to get it done. My goal was to prove the left side is the same as the right side. Here is me saying I did it. Now, some students will use QED. Another thing that is used often is a square that's colored in. So I don't care which one of these you use at the end of an identity, but you should put one of them at the end. Now, it seems silly right now to put something like this, but as you work through this unit, I think that you'll find that sometimes writing that QED or putting that square and coloring it in is very much a celebration at the end of an equation. Suggestion number 3 says if one side contains more than one function, while the other side contains only one, change the functions on one side by means of the 8 fundamental identities to the function on the other. So we're going to do an example of this in example number 2. In example 2, I already have this set up. So the left-hand side of my equation is over here, the right-hand side is over here, and I need to determine which side is more complicated. So this one's pretty easy. My left-hand side is more complicated. We're going to work on that one. Now, suggestion 3 says that if one side contains only one function and the other one contains more than one, try to rewrite it so that we have them all the same. So when I look at this, I have secant and tangent here, but only secant over here. So my goal is first going to be to get rid of this tangent squared theta and somehow turn that into a secant theta. Now, when I look at tan squared theta, I'm going to go to my identity sheet and I'm going to see, where do I see tan squared theta? Anytime I see a squared, my first place I'm going to look is going to be my Pythagorean identities. And I do have a Pythagorean identity that is there. So tan squared theta is actually equal to secant squared theta minus 1. Now, sometimes you'll have to manipulate those identities because they're not written exactly like that. So you might have to move them between different sides to make it exactly equal. But we know that we can manipulate those equations like we do in other classes. So I'm going to have my base of, I'm not touching this secant squared theta, I'm not touching this plus secant squared theta, but this tan squared theta, I'm going to rewrite as secant squared theta minus 1. Now I put it in brackets because I need to remember that secant squared theta is going to be multiplied by it. So I need to make sure that I'm distributing it into those brackets and I'm doing this properly. So my next step is going to be that distribution. So I'm going to take secant squared theta, I'm going to multiply it by secant squared theta. That's going to give me secant to the 4 theta. Secant squared theta times -1 is negative secant theta. And this plus secant theta is going to just continue to come down. Now I'm going to look at what I have. Secant to the 4 theta minus secant squared theta plus secant squared theta. When I look at this, I see that I have secant squared theta and secant squared theta, where one is positive and one is negative. So those two things are actually just going to cancel each other out. When I do that, I'm left with only secant to the 4 theta, and my left side is now equal to my right side. So QED, or colored in square, I have proved this identity. Suggestion number 4 states that if the numerator of one side contains several terms and the denominator only one term, then sometimes the proof can be accomplished by writing that side as a sum or difference of several fractions, each of which contain the original denominator. Then, by using some of the 8 fundamental identities, you may be able to complete the proof. So here I have my equation set up already. And so you'll see here is cosecant squared theta plus sine theta, and the much more complicated side of cotangent cubed theta plus cotangent theta plus cosine theta. Now, something I sometimes see students do is they try to add cotangent cubed theta plus cotangent theta. Now, we can't do that because that would be like adding x cubed plus x, and those are not like terms, so we can't combine them. But we are going to use suggestion number 4. So this tells us that we're going to rewrite this as a sum and difference of terms. So I'm going to take each of the terms on the numerator, cotangent cubed theta, for example, and write it over cotangent theta. And I'm going to do each of these individually, so I can actually break it up. Now, this allows me to do some simplification, which is going to make this a lot easier. So when I look at each of these, cotangent and cotangent, well, those are the same, so I can actually cancel these out. So I have cotangent on the bottom, and that can get rid of one of the cotangents on the top. And that's going to leave us with, instead of an exponent of 3, an exponent of 2. In the second term, cotangent and cotangent, well, that's going to cancel, and I'm going to be left with just 1. And the last one here, there's not a whole lot that I can do with that. So we're just going to hold on to it and work with it in the next step. So when I rewrite this, this here is going to simplify to just being cotangent squared theta plus 1. And I have this tag along that I couldn't really simplify, but we're going to continue to work with. So now I have this, and reminder, my goal is cosecant squared theta plus sine theta. So I'm going to look, cotangent squared theta plus 1. Now, when I have something squared and I have a 1, that tells me, hey, those look like my Pythagorean identities. Let's take a look at those and see, can I get something that I'm looking for over here through cotangent squared and 1? Now, when you look at your identities, you'll actually find that cotangent squared theta plus 1 is directly equal to cosecant squared theta. So I already have half of my goal here. Once I do that, I'm going to have to take a look at this. Somehow I need to turn this into sine theta. The first thing I'm going to do that is I'm going to rewrite cotangent using my quotient identity as cosine over sine. So it's going to look a little bit like this. So this here is what I'm working on, cotangent theta is going to turn into cosine theta over sine theta. Now, this here, sometimes I find students will highlight it because that tells them don't touch that anymore. I have that where I want it to be. I only need to fix this piece. If you choose to highlight it, that's awesome. If you don't, also awesome. So I'm going to bring that cosecant squared theta down to the next step. And I'm going to look at this and say, you know what? I have a fraction within a fraction. So I'm going to say, when I divide fractions, I multiply by the reciprocal. So I'm going to have plus cosine theta times sine over cosine. So I've done the reciprocal of my denominator, and I need to simplify. So when I simplify, I'm going to have that my cosine on the top and my cosine on the bottom are going to cancel. And what am I left with? This golden sign. So my final solution, this has been proven to be equal to cosecant squared theta plus sine theta. And QED. Suggestion number 5 tells us to look for opportunities to factor expressions. The next step may then be apparent. So I have my next example set up. I have the left side over here and the right side over here. And when I look at this, I look at and see, you know what, I have a fraction over here. That is way more complicated than no fraction, so I'm going to work on this side. Now, my suggestion is to factor. So my denominator, I'm going to start there. It doesn't have anything in there that I can factor. Cosecant and sine, there's no way that I can factor something out. Now, on the top, or on the numerator, I have cosecant cubed theta plus sine cubed theta. Now, I'm going to focus in on this piece. Something that we do cover in other courses and previously in our curriculums is how to factor sums and differences of cubes. This is something that we don't explicitly cover anymore, but I will go over roughly the short form of it. So basically, when we have a sum or difference of cubes, we are going to, for example, x cubed plus y cubed, which fits our example. That is going to be x plus y times x squared minus xy plus y squared. So I'm going to go over this in class, hopefully before you actually do this section, so that you have an idea of how to do that short form factoring, because there will be a couple of questions, but nothing on in an assessment. They'll mostly just be textbook questions that you'll do with this that may continue that or contain that sum and difference of squares, of cubes, sorry. So using this idea here, cosecant cubed theta plus sine cubed theta is going to work out to being cosecant theta plus sine theta times cosecant squared theta minus cosecant sine theta plus sine squared theta. So this is just following this pattern that I have over here. I'm not doing anything with my denominator, so it is going to stay just the way that it is. Once I have that done, I can take a look and see, is there anything I can do to make this a lot simpler? So I'm going to take a look what I have on the top. I'm going to take a look what I have on the bottom. I'm going to notice, hey, cosecant theta plus sine theta is located here, but it's also located here. So because these are multiplied, I can cancel that out top and bottom. And it's going to cancel to being 1. Now, if it was an addition or a subtraction sign in here, I would not be able to do that, but it's multiplication, so I'm good to go. This is going to leave me with only cosecant squared theta minus cosecant theta sine theta plus sine squared theta. So I've gotten rid of that fraction. That is a big step. I'm going to look at what I need. I need cotangent squared theta plus sine squared theta. Well, I have the sine squared theta. So this is where you might pull out your highlighter and say, hey, this piece here, don't touch it. I know that I have it. I need to work somewhere in here. So I'm going to look at this middle piece first. I'm going to say, hey, you know what? This here is something, they're related functions. cosecant is the reciprocal of sine, so I'm going to use that to simplify here. So I have this cosecant squared theta, and the minus is going to come down, my sine squared theta is going to come down, and I'm going to rewrite this using the fraction. So cosecant is 1 over sine theta, and I'm going to multiply that by sine theta. Now, this has sine on the top and the bottom, so I can cancel here, and I'm left with just 1. So when I do this, I'm going to have cosecant squared theta minus, this simplifies to just being this 1, plus sine squared theta. So I'm getting close. I have this cosecant, or the sine theta. I just need to turn cosecant squared theta minus 1 into cotangent theta. Now, I have a squared and I have a 1. So that tells me, let's look at my Pythagorean identities. So cosecant squared theta minus 1 is going to be equal to cotangent squared theta using those Pythagorean identities. So I'm going to have cotangent squared theta plus sine squared theta, and I have shown that the left side is equal to the right side, and QED. Suggestion number 6 states that it may sometimes be necessary to multiply the numerator and the denominator of one side by the same factor in order to obtain the desired proof. Now, I often summarize this as sometimes we need to multiply by a really silly form of 1. So I've set up my equation here, 1 minus cos theta divided by sine, and sine theta divided by 1 plus cosine theta. Now, it's hard here to decide which one is more complicated and which one is easier. In this case, I'm going to help you out. We're actually going to start on the left-hand side, but this is possible if you start on the right-hand side as well. Now, suggestion 6 says that we need to multiply by a silly form of 1. And sometimes determining what that silly form of 1 is going to be is difficult. Now, my suggestion to you is, if we're going to start here, I would multiply by sine theta over sine theta. So this is just 1. I'm not changing the value. It's just a silly form of 1. If I wanted to start here, I would probably multiply by 1 minus cosine theta, because that would create some squares in there, and it might work out to go this way. As we go through, you might be able to see why I would choose that by reflecting back. But typically, I'm going to start over here, and we're going to work from there. Now, once I integrate this, I need to multiply it in. So I have that I'm going to have 1 minus cosine theta sine theta on the top, and sine squared theta on the bottom. So sine times sine is sine squared. What I'm going to do from here is I am going to look at this sine squared theta. My denominator is not matching this at all. My numerator's starting to get there. I have a sine theta on the top. I also have this that I need to get rid of, but there's no obvious thing I can do with that. So let's look at that sine squared theta. Now, I'm not touching the top, so it's going to stay there. But this sine squared theta, I know when I see a squared, I'm going to go to those Pythagorean identities. And when I look at my Pythagorean identities, I'm going to see that sine squared plus cos squared is equal to 1. So when I manipulate that a little bit, I can rewrite this that sine squared theta is the same as 1 minus cosine theta. Now, this is starting to look a little bit more promising. I have something here where I might be able to get rid of this if I start thinking creatively. My sine is what I need, and I need something kind of like this on the bottom. So I'm going to take a look at this denominator, and I'm going to see what can I do with that. Now, we are going to use suggestion number 5 here, and we're actually going to factor it. So you'll look at it and you'll notice that 1 is a perfect square, cosine squared is a perfect square, and I have a minus sign in the middle. So I'm going to factor this by difference of squares. So my numerator is going to stay the same, and my denominator is going to follow the pattern that we learned in Foundations 10. So the square root of the first minus the square root of the second times the square root of the first plus the square root of the second. Now, when I look at that, I have some nice things here that, I missed a bracket, that cancel out. So 1 minus cosine theta on the top, 1 minus cosine theta on the bottom. This is awesome. I can get rid of it. My numerator is now exactly the way I need it, and I'm only left with 1 plus cosine theta on the bottom, which is precisely what I need my denominator to look like. So by multiplying by a silly form 1, doing some factoring and some canceling, I have QED, proven that this is an identity. Suggestion 7 states that if none of the preceding steps seem appropriate, then rewrite all functions on the more complicated side in terms of sine and cosine and simplify the resulting expression. So I have my expression set up, left side, right side, and when I look at it, there's not a whole lot in common. I don't have a tan over here. I do have cotangent, which might be something I might try out, but because this is after the suggestion, we're not going to go down that path. There's nothing that I can factor. A common form of 1 is probably not going to help me. So I'm going to look at each of these terms and rewrite them in terms of only writing sines and cosines. So I'm going to take this cosecant theta and I'm going to rewrite it as a 1 over sine theta. This minus 1 is going to continue here. And I'm going to take in my second term, cotangent squared theta, and I'm going to rewrite that as cosine squared over sine. So now I have everything written only with sines and cosines. Now we do that because that often is going to allow us to simplify because everything is more or less the same function written down. So once I get to here, again, I'm kind of challenged. So I'm going to do one thing to this side and another thing to this side. Now, if you want to do them separately, I encourage you to do them separately. However, I'm going to sort of work both terms of this at the same time. Now, this term here, the first term, there's not a whole lot I can do. So I'm going to actually multiply the denominator by a funky form of 1 or a silly form of 1. Now, I know to do this because I've been doing this for a really long time. This will come with additional practice as you move through these types of questions. So when I do that, my numerator is not going to change. I still have sine theta on the top. And I'm only multiplying this 1 by sine theta over sine theta. Now, the reason why I'm doing that is going to be a little bit more obvious here. So when I do this, I'm going to have 1 over sine theta minus sine theta over sine theta. Now that my denominators here are the same, I can actually write it as the one fraction. So I have sine theta over 1 minus sine theta, sine theta. So I've taken this chunk here and I've rewritten it, combined that fraction into 1 minus sine theta over sine theta. On the other term, I'm going to look at the fact that I have a fraction and I have another fraction in there, so I'm going to multiply by the reciprocal to try and get rid of that fraction on the bottom because it's not really that fun to work with. And so I'm going to have sine theta times the reciprocal, or sine squared theta over cosine squared theta. When I do that, I'm going to combine sine theta times sine squared theta is going to give me sine cubed theta, and cosine squared theta is going to be in my denominator still. So it's a little bit more complicated than what we started, but we're starting to work towards some of the ideas of what we might need. Now, like I'm divided or multiplied by the reciprocal here, I'm going to do the same thing here to try and get this so I have one fraction and one fraction, because when we have these fractions inside fractions, it's not very fun to work with. So I'm going to multiply by the reciprocal, so sine times sine theta over 1 minus sine theta. My left or my right term is going to stay the same. And as I simplify, I'm going to get sine squared theta over 1 minus sine theta minus sine cubed theta over cosine squared theta. Now, I'm looking at this and trying to figure out what I can do. And again, I'm kind of stuck. So one of the things that I can do is I can try to write this all as one fraction. And in order to write it as one fraction, I need to have a common denominator. So to do that, I'm going to multiply this fraction here by a silly form of 1. And that silly form of 1 is going to be cosine squared theta over cosine squared theta. I'm going to take the denominator of the opposite fraction and multiply it here so that I have cosine and 1 minus sine in my denominator. And I'm going to do the opposite over here. So I'm going to multiply the second term by 1 minus sine theta over 1 minus sine theta. Now, remember, this is just a silly form of 1. I've written it in a really complicated way in order to achieve something within my equation. Same with this one. So when I do that, I need to then complete that multiplication. So I'm going to have cosine squared theta sine theta squared theta minus sine cubed theta times 1 minus sine theta. And that is all going to be over cosine squared theta times 1 minus sine theta. So I've written this as one fraction. When I do that, it's going to give me a few more options. So I'm going to next distribute this sine cubed into this set of brackets. And so when I do that, I'm going to have cosine squared theta, sine squared theta. Here I've taken sine cubed times 1 is sine cubed, and sine cubed times sine theta is sine to the 4. Now keep in mind, watch your signs as you're doing this because they are going to be important as we go through here. Now, next thing I'm going to do is I'm going to need to factor out a common sign. So I have sine in this term, sine in this term, sine in this term. And I can actually take out a common factor. Oh, my denominator needs to stay there. Sorry, guys. I can actually take out a common factor of that from sine squared theta. And when I do that, I will be left in my first term with cosine theta, squared theta, minus sine theta. So remember, I'm taking 2 out. That means 1 is left over. And I'm going to have plus sine squared theta in my second, or my last term there. My denominator, I'm not touching it. Leave it the same. So I factored out this sine squared theta. Now, I think it's important to note at this point in time that our goal is tan squared theta. And I'm almost there. I have this sine squared theta and I have cos squared theta on the top and the bottom, and that is what tan squared theta is equal to. So I just need to somehow manage to prove that this piece here is equal to 1. So the first thing I'm going to do in order to look at that is I'm going to see, look, I have a cosine squared theta and a sine squared theta. Both of them are positive, but they are separated. So the nice thing about this is I know they're both positive. I can actually use my Pythagorean identity here, and I can say, you know what, this piece here, cosine squared theta and sine squared theta, is actually going to combine together to give me just 1. So I'm going to show that here. So I have cosine and sine. That is being replaced with this 1. Minus sine theta is staying there, and my denominator is staying the same. Now, when I do this, I can see, hey, 1 minus sine theta on the top, 1 minus sine theta on the bottom. I can cancel those two things out. So I'm going to take and say this and this. Those divide out, they're going to be equal to 1. And that's going to leave me with sine squared theta over cosine squared theta. Now, something we haven't talked about is if I have the same exponent on both the top and the bottom, I can actually transfer that directly. So sine squared theta over cosine squared theta is equal to tan squared theta. Now, this would work the same if it was sine cubed over cos cubed or sine to the 4 over cos to the 4. You could show it by actually expanding it and then bringing it back down. But for the purposes of what we're doing, you can use that sine squared over cos squared is equal to tan squared. So we have actually, in this process, gone through and shown that that complicated fraction that we had at the beginning is equal to tan squared theta, which is QED. This is the type of question where often that QED is such a celebration that we're going to feel good about finally getting to write that down. Now, this section does not have textbook questions assigned to it. I don't really like the textbook questions, and so what I've actually done is I have a booklet of questions that you are going to work on that I have pulled from another textbook. So at this time, I'm going to ask you to grab those textbook questions and start trying them out.